All right, so this is part 2 of the 5.3 study guide, and I'm going to move on to page 4 of the study guide and see if we can finish this up. So, question 14 says, passing the light emitted by an element through a prism gives the, and the answer here is atomic emission spectrum. So I'm going to put in here atomic emission, and then I'm going to keep writing spectrum. Or what I called it, right, in the last video I told you, I call this, aka, spectral fingerprint. So I think of it as the spectral fingerprint. Okay, number 15. Is the following sentence true or false? The emission spectrum of an element can be the same as the emission spectrum of another element. Well, can you have the same fingerprint as another person? The answer is no, and so this is definitely false. That's what makes these emission spectrums so incredibly awesome, because anytime you see that emission spectrum, even if you're on another planet or another part of the universe, it's going to be the same fingerprint every time, and so you always know what element you're dealing with. Number 16, only electrons move from higher to lower energy levels and lose energy and emit light. So only electrons moving from high, I'll say higher, to lower energy levels lose energy and emit light, okay? It's when they're falling down off of those excited states, that's when they give off that light, okay? And by the way, those packets of light are called quantums, aren't they? And we've talked about that quite a bit already in some of the other sections. So let's move on to number 17. What did Albert Einstein call the quanta of light energy? Well, he called this light energy photons. So who came up with this idea of photons? Oh, that would be Mr. Einstein himself. So a quanta of light energy is called a photon. And there's a whole section of physics called optics, and we study photons like crazy. And there's a whole branch of chemistry where we do this too, and that would be looking at spectral analysis and things like that. So photons are very, very important in chemistry for us to use. So number 18, what is the lowest possible energy of an electron called? Well, if it's at its lowest point, then we call that a ground state. So it is at ground state. And that just means it's, it's at its lowest energy. It's not going to be glowing. It's not going to be doing anything. It's just kind of grounded, just kind of sitting there, just waiting to see what's going to happen next. So number 19, what does de Broglie's equation predict about the behavior of particles? Well, it predicts that particles are going to behave like waves, okay? So his equation predicts particles act like waves. Okay, and we kind of see that, electrons will kind of behave like waves, photons a lot of times behave like waves, and so this whole equation that we're not going to really get into too much in quantum mechanics, it's basically just kind of predicting that things behave like waves, okay? And we're going to kind of leave it kind of simple like that, because we're not going to go into it that deep. It's just not a good situation this year to get into it too much. So, but we're just answering the questions now, right? So, is the following sentence true or false? Quantum mechanics describes the motions of subatomic particles and atoms as waves. The answer there is a big fat true. Okay? That's what we do in quantum mechanics. We turn everything into what seems to be like waves. According to Heisenberg uncertainty principle, it is impossible to know exactly both what? The speed or velocity and the position of a particle at any time. So we're going to say the velocity. We can't really tell how fast a particle is moving, and we also can't tell its position. We can only kind of guess about where it's going to be, okay? We can, I can pretty much predict that most kids are going to be down in the cafeteria in period 5 at some point in time. But I cannot predict how fast you're going to eat your lunch, right? I just can't do it. I can just kind of get relatively close as to where you're going to be. I don't know which table you're going to be at. I don't know exactly, but I can kind of tell a region of where you're going to be. And that's about as close as I can get. Then number 22, does the Heisenberg uncertainty principle apply to cars and airplanes? The answer is no. It only applies, it only applies to very small particles. Very small particles, like electrons. Okay, like electrons. And then finally we're going to get into some guided practice down here at the bottom. I'm going to do a couple of these with you. It says, what is the wavelength of radiation with a frequency of 1.5 times 10 to the 13 hertz? Does this radiation have a longer or shorter wavelength than red light? Well, let's see. We're going to have to kind of go in here and look at this. I'm going to go ahead and make my triangle first of all. I know that I'm going to put C up here. I want to put lambda here, and I'm going to put the wavelength there. So here we go. What is the equation for frequency, or for the relationship between frequency and wavelength? Well, I just did it. It's going to be C equals lambda V. Okay. And what does C stand for, and what's its value? C is the speed of light. So that's the speed O, light. And it's going to be 3.00 times 10 to the 8th meters per second. That's just something you're going to need to know. And what is the wavelength of the red light in meters? Well, red light has a wavelength, on average, you'll have to kind of look at your thing in the book. Okay, there's a whole big chart that shows all the different nanometers, but when you do, you're going to see that red in general is going to be about 7.0 times 10 to the negative 7th meters, and that's going to be its wavelength. Okay, and let's go on to the next page here real fast. It says solve the equation for the unknown lambda. Well, let's see. I'm going to go back to my triangle. If lambda is what I'm searching for, then lambda goes here, and what's my equation going to be? That's going to be C over V, right? See how it's already like set up for me. So this is going to be my equation that I'm going to use. So let's go ahead and put that in over here. So lambda is going to equal C over V. Substitute the known quantities for the equation and solve. Well, let's see. We know, okay, well, that's kind of stupid. Look at that. They put C in here as 2.998. You guys, this is C right here, which is really, I'm just going to say over here, C is going to, for our class, it's going to be 3 times 10 to the 8th. Okay, you don't have to get all crazy with the 2.998 times 10 to the 8th. It's really 3 times 10 to the 8th. Jeez, they get all picky about it, don't they? Okay, so what am I going to put where? I have to put the V in. So let's go back and find out what the V is. Again, I have to go back to the question. 1.5 times 10 to the 13 hertz. So come back over here. 1.5 times 10 to the negative 13 hertz. Okay, and then what's my answer going to be when it's all said and done? Well, if I do that, it's going to end up as 2.00 times 10 to the negative 5th, and that's going to be in meters. Well, that's going to be my wavelength right here, see? That's the new wavelength. So now compare the answer with the wavelength of red light. Does the given radiation have a wavelength longer or shorter than that of red light? Well, this is 2 times 10 to the negative 5th. The other one, if I can go back to that page, was 7 times 10 to the negative 7th. Which one is longer? Well, you know what we're going to need to do? I'm just going to write this out so you can kind of look at these numbers. Let's kind of spread this out here. This one is going to be 2, and then it's going to have negative 5th, right? So that's going to be 1, 2, 3. Let's see. If I put that there, that's going to be 1, 2, 3, 4. So I need one more. That's going to be that one, right? That's this one up here. The other one is going to be 7 times 10 to the negative 7th. So that's going to be 1, 2, 3, 4, 5, 6, 7. So there's the other one. Which one is going to be bigger and which one is shorter? Well, if we look at this, this has a quite a bit shorter wavelength than this does, doesn't it? Because this number is, if I could just say this number is bigger. And because it's bigger, it's going to have a longer wavelength. That's a longer wavelength. This one is shorter, so it's going to be smaller. This has a smaller wavelength. So does the given radiation have a wavelength longer or shorter than that of red light? And the answer here is that it has a longer wavelength than red light. And you know what that means? That means you cannot see it. You could not see this. This color is a color you can't see. It's too deep of a red for you to even see it. So that would be more probably in the, I don't know, in the infrared spectrum or something like that. It's going to be invisible to your eyes. You're not going to be able to see it. Okay, now let's look at this. Explain why you think this result makes sense. Well, we just did the math, right? And everything worked out. So I don't know, I just say we mathed it. We mathed it. And yeah. I don't know, I'm being a monster right now, but yeah, I mean, it just shows it. So are the units in your answer correct, and how do you know? Yes, we use meters. Meters is the SI unit for length. And then you could say, like, also known as wavelength. Okay, so there it is. All right. Whoa, what just happened there? That was weird. Off-ball principle. The things down here below are just going to be reviewing some of this stuff, and I'm going to finish this up, and then I'm going to let you guys do the self-check activity on the last 2 pages, okay? So down here, applying for the big idea. Off-ball principle is what? Basically, it says electrons fill lowest energy first. Lowest energy levels and orbitals first. And the way I described that in class was, you know, Walmart parking. Remember, when you go to Walmart, where are you going to park at? You're going to try to get to the closest to the doors you can, right? You don't want to walk 14 miles. So you try to get as close as you can to the front door. Well, the same thing with the off-ball principle. We always fill these guys first, and then we go from there, because this is lowest energy. This is closest to the door, and this is highest energy over here. And so we go to that one last. Pauli exclusion principle. Well, what is that? That basically, that one's easy. That's just no more than 2 electrons are in Whoops, hold on. Cannot type or write. Oh, I'm so bad. No more than 2 electrons in any orbital. So every orbital can only contain up to 2 electrons. Not too hard to figure out, right? And then finally, Hund's rule basically says that spins are always up. Well, let's say it a different way. Say it a different way. I think that would be confusing to especially the virtual students at home. So basically, let's say electrons spread out among shells and try to fill each orbital with 1 before filling with 2. Oh, it went back. Before filling 2. I don't know. I didn't say it very well. I don't know. How else can we say this? Yeah, I don't know. You just kind of have to do that first. So, not a big deal. You can finish up these. Don't forget to do them because I will be watching to make sure that you did. So these are all review questions right here, okay? This is the review before you take the test. By the way, tomorrow, Thursday, I'm going to be giving you a review quiz. That's worth some points. You want to make sure you do it. You'll have unlimited tries to take it. And then finally, on Friday, we will be taking the actual Chapter 5 test. Okay, so make sure that you get all these review questions done and then turn this in. It's due on Sunday, November the 8th by midnight.